Can you write with that? No, I can't write it here myself.
All right, guys, so we're talking about continuity today, which you've talked about before in Algebra 2, and we reviewed very, very briefly last time with the jumps on the graphs. There's three types of discontinuity. There's holes, jumps, and asymptotes. This first graph here, that's a hole, because there's, as you can see, a little hole in the middle of your graph. What we talk about is proving that you have to talk about the limit, like the graph approaching that value from either side. But first, we're starting with just discontinuity. So if I label this as A on my x-axis, I can say f of A is undefined. I can also say f of x is not continuous at f of A. All right, right? We can see that that's not a continuous graph. Like visually, you just look at it and you can say, okay, I see there's a hole in the middle of that graph. Now, the second one, there's A again. So this time, f of A is defined, right? There's actually a function value at A. It's just not in my line here. So f of A is defined. However, f of x is still not continuous, okay? And I should have just said at A over here, not. Okay. So at that specific x value, right, there's a function value. Like if I said, what is f of A, you could tell me, I don't know, whatever it is, 1, 2, but the function itself is still not continuous. So when you're proving continuity, you have to be able to put all those pieces together. Like, is there a function value? Is your graph approaching that function value? To do that, we have to know what a limit is. So this is where we're actually starting some calculus stuff. The first part of calculus will be limits and derivatives for you next year, whichever one you take. Bless you. What? Nope. Finn?
What do you think by like define or something?
Like if I said, what is f of 2 here? What would you tell me?
It's not like there, it's a whole.
Right, so there isn't one. What if I did that? Now what is f of 2? Okay. It's defined. It has a value. That's all it is. All right, guys, so limit notation. We write the limit of f of x as x approaches, we're using A in this case, it's some number. And then it equals whatever the y value is. So in this case, that's L, right? I'm using this picture over here to write my limit from. So the limit of f of x, that part stays the same. The x approaching whatever x value we're talking about. What it equals, this over here, this is your y value. So you're looking at a graph and saying, as I sort of close in on this x value, what y value am I getting closer and closer to? It's all about what you're approaching. It doesn't have to be what it equals at that exact point. It's what are you getting really, really, really close to from either side. So like this graph I drew over here, if I asked you the limit of f of x, pretend that's f of x, as x approaches 2, you look from either side. So like I'm closing in here and here. You see it? So what y value is it getting really close to? You'd say that's 1. Okay. We can see this in a table. We're not going to use a calculator in this skill guide. This is just what your calculator would show you if we were doing them that way.
How much is
I don't think it would even help you. You would just be like not knowing what you needed to plug in. So let's say this is the equation y equals x plus 3. That's our first equation. Just so you have an idea of where these calculator things came from. And let's say our second one is x squared minus 9 over x minus 3. Yeah, we're just kind of filling in as we go through the pages here. So what we're looking at, if I ask you the limit as x approaches 3 from this table, and we're going to do it algebraically down here as well. And we'll do y1 first, the same for both. So as I get closer and closer to the x value of 3 here, what are your y values doing? Getting closer to 6. And it's the same for both of our equations here. That's all a limit is. It's 6. It's what are we approaching? What are we getting really, really close to? Sometimes you can just plug the number in, like, oh, my x value is 3. I plug it in and I get 6. Great. If it's undefined at that point, though, you can't just plug it in. So that's where we do the approaching. What are we getting really close to? So we're going to look at these. We're going to actually make the graphs and look at these down here. So again, we'll use x plus 3 for our y1. How do I graph the line y equals x plus 3? Okay. Looks like there's 3, right? And then we'll pretend that I have a slope of 1. All right, so let's say, and my x value of 3 is over here. Obviously, my graph is not perfect, but algebraically, can you see as x approaches 3, like what are we going to get close to here? What y value are we approaching? 6, right? And again, if you can just plug that 3 in, if you can go, well, what do I get when I do 3 plus 3? You get 6. That is the limit. That's okay. Some of them are that simple. Completely fine. Plug it in. There's your limit. Now let's think about if I do the second equation of x squared minus 9 over x plus 3. Well, what does x squared minus 9 factor into? It's minus 3x plus 3.
X plus 3 x minus 3.
It should say minus, thanks.
On the bottom.
Yeah, I wrote the wrong one. Too many 3s. Okay, what cancels? Okay, what does that create when that cancels out? A whole, good. So I'm left with just y equals x plus 3, but I know I have a hole at 3 comma what? How do we find the coordinate? Yes, plug it in. So we get 3, 6. So very similar line to the first one, right? Except we have that little, and I should make that more obviously, an open circle. We have our hole happening there. The hole does not change how we evaluate the limit. What are we getting close to? Like, what's the y coordinate of that hole? What's happening? 6. Yes, that is it. Okay. If you're getting that, you get a huge part of what's happening with limits, okay? It's not that bad. All right. I guess you don't have to turn the page. I have to turn the page. Okay. Lots of words, not that much that we're actually doing on this page. So we're going to use this little weird graph over here, this interesting piecewise graph, and you are going to evaluate some limits for me. So I want you to look at that function, that's f of x, and try to tell me what is the limit as x approaches -5, what is it as x approaches 2, as x approaches 0, and as x approaches 4. So try those, talk to each other. I will take attendance. I know, it's very hot in here today.
An obnoxious fan.
Oh, that's right, yes.
Unlimited calling Luther test, but instead he's another summoner today. So now we have 2 summoners. We have some random DB2, but he didn't tell us what unit it's on. So it could be any unit, I think.
Just a surprise. Surprise us.
I don't know. I think he said it couldn't be on unit 1, so I think so.
Really narrows it down.
Right now.
All right, guys, let's go through them. Letter A is x approaches -5. What did you guys get? 4, yes. What about as x approaches 2? 3. Do we all agree that it's 3 and not 5? Yeah, that little dot up there is just there to mess with you. If I had asked you what is f of 2, like the function value at 2, then you would say 5. Okay, but as far as limits, like if you're this little guy walking along the graph here, right, here you are hiking up this mountain, are you approaching 5? No, you're approaching 3, right? Okay, that's been visualized, some guy out hiking every time you're evaluating limits. Okay, what did you tell me for C? The limit does not exist. Okay, it's your Mean Girls moment here. D and E, we can write, does not exist. So
not NA.
Wait, why doesn't it?
okay, so let's again be our little people out hiking. So this guy's over here. He is approaching 0 from the left. Okay, this left and right business is going to matter soon. So he's approaching from the left. What y value is this guy getting close to? 0, right? Okay. His buddy's over here approaching the x value of 0. I know, he's a serious rock climber. What y value is he getting close to? 8. Do 0 and 8 match? No, they do not. Okay, so if your left-hand limit and right-hand limit are different, the overall limit does not exist. Okay, they have to run into each other, otherwise the limit does not exist.
If you draw another 0 below this 0, then it's
True. Still not 0 though. Or still not 8. They still don't match. All right, what'd you get for letter D then? 0. Okay, we had like the tricky one and then back to an easy one. All right. We're going to look a little more closely in the whole left-hand and right-hand limit. Okay, so this notation, I know it's really small on your worksheet. Do you see that tiny little negative next to the A? You guys are young, you can see. Maybe.
On a good day.
Adam's not here without his glasses, so I don't know.
Is it not an exponent?
It looks like an exponent, like the negative is up where an exponent would be, okay? That just means we're talking about the limit only from the left-hand side. So we would say the left-hand limit as x approaches a, or the limit of f of x from the left as x approaches a, all of that. But just know that little tiny negative means from the left. So down below, do you see the little tiny plus sign up there? That means from the right. So guys, if you're not good at your left and rights, we got to work on that, okay?
Wait. So if we were given whether left or right hand limit on the denominator,
Yeah.
it would be the answer.
Yep, it would have been either 0 or 8. Yep. And then I might have said, what is the limit as x approaches 0? And you'd go, oh, those were different. It doesn't exist. Yes. All right. Let's talk about this function now. We've got the limit as x approaches 0 of the absolute value of x over x. It's not one you guys are used to graphing every day, but do we see how just plugging 0 in is not really going to work? Right? We'd have a 0 in the denominator. That is not okay. So we need to think about what this graph looks like. This is really the best picture of it over here. If I plug in any negative x value, I just get -1 for my y value. But if I plug in a positive x value, I get +1. 0 is a whole for both of them, okay? So, as x approaches 0 from the left, so your guy is here just out for a stroll today. This is not much of a hike. Nice and level. It is. So your notation on this, move this out of the way. We would say the limit of, we'll assume this was f of x, as x approaches 0 from the left is equal to -1. I know you guys have like the tiniest line to write that on, so. Yep, it looks like 0 raised to the negative. Yep. Yes, yes. Yes, they will not be this tiny on your test, but this would have been like 8 pages, and I just didn't, yeah. Saving some trees. So guys, do you think you know how you'd write it if it's from the right? Yeah, okay, let's write that in here. Limit of f of x as x approaches 0, little plus sign. That one's going to equal +1.
So if you write it with no plus or minus sign,
that means like the overall limit where you're looking at both sides. So that's what we were doing, like
so
up there.
with like the graph above, right?
Mm-hmm.
Did you say if like for the graph above, limit f of x as x approaches 0, it's raised or like from the left equals 0?
Mm-hmm. Yeah, and if it was from the right, it would have equaled to 8. Yep. All right, guys, so little generalization here. The limit of f of x as x approaches a equals capital L here, equals whatever the y value is, if and only if, do you guys remember this IFF from geometry?
No,
You can-
like Albert said.
All right, you can write out if and only if you would like to. If and only if the limit of f of x as x approaches a from the left equals L, it's whatever the limit is. And the limit of f of x as x approaches a from the right also equals L. So the limit without any plus or minus, so not from the left or right, just the overall limit, that only exists if the left-hand limit and right-hand limit equal the same thing. Okay. Oh, are we out of tissues? There's some on the back. And then I'll get more out of the cabinet. Oh my gosh, allergies are terrible right now. Yes. All right, guys, I think you finally get to turn your page.
Answers.
God. All right, guys, so again, more limit practice here, and pay attention. It's 2 with a little negative, 2 with a little positive, and then just 2. Okay, now your magnifying glass here.
Right? I can't even see the word.
I know, they're small.
I can't see what my glasses are. I did not wear my glasses today. All the data that shows. No. Can we take quiz off and put NA on the test instead of...
Yes, D and E is what we need.
What do we put done?
Oh, we need D and E.
I'm not going to remember that.
Wait, so whoa.
I look away.
I'm so sorry. I'm so sorry because I really dislike this there. I'm so sorry. Dude, I'm so sorry because I really dislike this. So that was completely my bad. I apologize. I really.
All right, ask your question. It's okay.
I missed the late, so C would be does not exist. Okay.
Yeah.
No, 'cause I was talking to him about this thing, so then I was like, oh my mind.
You caused an uproar.
That was the biggest mistake I
I don't
made
even
in
know
my
who
life.
his name is.
I don't know where it is.
I've heard the name, but I don't know.
No. You don't want to know.
Are we ready, guys? All right, 2 from the left. What is it? 2 from the right. So 2 does not exist, right? 3 and 1 do not match, correct? Those are different numbers. So does not exist for that overall limit then. So 2 from the left. Okay, I'm drawing a wall at 2. Okay, as I approach that wall from the left,
It's not the
you
actual.
clearly need to draw your hiking man, and then you've got it.
No.
We're gonna see this all over our tests.
I know, just little people, little rock climbers everywhere. It's great. All right, so letter D. What about 5 from the left? 5 from the right? So 5? 2. Okay. We got it.
I'm sorry.
Just a side note over here. What if I had asked you G of 5? What would that equal? 1. Yes. Okay. We see the function value is different than the limit. Okay. Limits are the journey, not the destination. Okay. Continuity test. 3 bullet points. Not 5 like your previous. Remember when you guys hated doing that?
3 bullet points I can't read.
Yeah, I know. They're kind of blurry. What's the function value at 5?
Your eyes go out of focus and it's just like...
So when x is 5, what do we get?
1.
Yes.
Why is there like a red line then?
I was helping them. Okay.
Your
All right. I don't know why that's so blurry, guys, but it is. So a function f of x is continuous at x equals c if it satisfies the following conditions. 3 bullet points. You got to meet all 3. First, f of x is defined at c. That just means the function exists at whatever x value we're talking about. Then the second bullet point, f of x approaches the same value from either side of c. So that just means the limit exists at this specific x value. And then the third point is that the first two bullet points are the same thing. So the function exists, and that value is the same as the limit at that specific point. Okay? We'll go through these together so you can see. So the first one here, I've given you, oh, these are spaced really strangely. So number 3, determine whether f of x equals 1 over 2x plus 1 is continuous at x equals 1/2. Justify with the continuity test. So first bullet point, we need to find f of 1/2. So if I plug in 1/2 to f of x, what do I get? I get 1/2, right? Yeah. Okay. So first bullet point, does it exist? Yes, there is a point there. All right, second bullet point. I am looking for the limit of f of x as x approaches 1/2. Okay, this is the x value we've been told to look at. So as x approaches 1/2. Nope, just the overall limit. So, a couple of things here. You can try to visualize the graph. You're like, great, graphing rationals. We know this is bottom heavy. It's got this horizontal asymptote. Guys, where's the vertical asymptote with this graph? -1/2, so somewhere over here. And then I've just got my nice normal, like lovely rational graph going on there. So is there anything weird happening at +1/2? Like, is there any strange things, holes, asymptotes, anything at +1/2? There's nothing happening there. So the limit is going to be the same as the function value, right? Like, as I follow that little graph, isn't it going to just approach whatever the function value is there? Yeah. Okay, so that's also 1/2. Had a lot of halves in this problem. So the third one, did the first two bullet points equal each other? Yes, so we would say f of 1/2 equals the limit of f of x as x approaches 1/2. Therefore, the 3 dots, f of x is continuous, and we can abbreviate at x equals 1/2. Now, we're not saying the entire graph is continuous, because it definitely isn't. But at x equals 1/2, yes, the graph is continuous. Yeah, we'll do several more. I know it's kind of a weird, redundant process on this first one, especially.
So if there isn't a hole,
Or an asymptote or a jump, like anything weird. Yeah. Yep. Yeah, basically, if you can plug in the x value, that is your limit. So. All right, so let's look at number 4 here. This time we have a piecewise function, and it was not specified in the directions, but I should be asking you, is g of x continuous at x equals 0? We lost our directions here. We have to go through, well, I'll show you. You don't do the whole thing on this one. Okay, so we start with our bullet points. The first one, we find g of 0. Interesting. Can I find g of 0? No, does it exist? So g of 0 does not exist. Yeah, you can say D and E. So if that point doesn't even exist on the graph, what do you think that tells us about continuity? Yeah. Therefore, nope, if one doesn't work, you stop.
So therefore, it's 3 dots kind of.
Yeah, kind of like a triangle of 3 dots. All right. So we like those. Those are quick when they're not continuous. Okay, let's try again here. This one, again, we lost our directions. Is h of x continuous? I'm not going to ask you at 2, because if it was 2, what would you tell me right away? Yeah, same as last time. Okay, let's say, is it continuous at x equals 0? So our first bullet point, we start with h of 0. What do we get? Yeah, guys, how do I know which piece to plug it into?
The one that's left.
Yeah, so I plug it into the first one. So what do I get? -1. Okay. Now the limit of h of x as x approaches 0. Okay, again, we would still be looking at this piece up here, right? Because that's where that would be. 3x minus 1. Guys, is there anything, like, interesting with that graph? No, nothing notable. It's a line. So what do you think the limit is as x approaches 0? -1, right? Same thing. Did they match? Yes, so your third bullet point is to tell me that h of 0 equals the limit of h of x as x approaches 0. Therefore, yeah, he's died. Adam, I hope you're watching the video.
Send him a message or something to figure out if you watched it.
Yeah. Should we ask him a question?
YouTube video go viral, so then it pops up and it's like recommended.
I'd be like, what?
1.3 billion views.
If you repeat this word back to me on class.
If you guys want to watch this video, you'll get a free Nintendo Switch.
Oh my.
Just skim everybody watching.
All right, guys, questions so far? Yeah. So 3x minus 1, like, that's what the graph is, right? So -1, 3 over 1, and let's see. It goes to 2. Okay, that's the line, right, that we're talking about. So if I ask you, as x approaches 0, my graph's a little off, what y value is my graph approaching? Yes. Okay, you can make the graph, but if it's not like a weird graph, like if there's nothing strange happening, you can just plug in the x value and that tells you the limit. Okay. It seems too simple, I know. All right, guys, discontinuity. 3 types of discontinuity. Oh, is this the right order? Yes, okay. So, infinite discontinuity, guys, that is an asymptote. That happens when the denominator equals 0. Okay, so looks like that. You know what asymptotes are. Here. Our second type is removable discontinuity. That's just when you have a hole. That happens when you have a common factor. Guys, we only have 10 minutes left.
What?
That's funny.
No, wait, no, it's like 1920, right? You said like 909.
Oh, good. Okay, it's not 59. I had the wrong 9. Good. We might finish.
What happens if we didn't?
Yeah, we can just stop and like.
Why did you even have to? Well, no, she would have figured it out around that. But you're right.
So graphically, guys, that's what a hole looks like. A jump you usually see in piecewise functions.
Pi what?
Piecewise.
Oh.
P-I-E-C-E.
I thought it had the pi.
It does have pi in it. So guys, that's a jump. Having an open circle on the end when you have a jump does not make that a hole, guys. Okay, a hole is when you've got like points on either side of it and then you just have a hole.
Examples, right?
Yeah, those are just random pictures for you.
Are those supposed to be like the same?
X value. Yeah, and they won't always be, but usually they are.
Jump.
We're gonna jump around a little here, guys, to make sure we finish.
That's a lot of numbers.
That is a lot of numbers. I don't think I want to do both of these.
Yeah, I don't think we want to do that either.
Oh, those
No,
are
no, it's easy.
for all 6 questions.
Why is it formatted so?
I don't know.
Okay, so
Okay, guys, try number 8 for me. 7, this would need to be not even, anyway, that's weird. Try number 8 for me. Find the value of k such that the functions are continuous. Well, what would we need for it to be a continuous function? Yeah, like, yes, this, hey guys, up here. Yes, this is a piecewise function. But for a piecewise function to be continuous, what I need is like for one piece to run into the other piece, right? Okay, so algebraically, what would that mean with these two equations?
Wait, I drew the graph.
Oh, the graph, that was just me randomly making a picture for you. Oh, scribble it out with your carrot pen. It'll be okay. What has to be true about these two pieces of my equation? So they're going to equal each other at what x value? Yes. So I'm going to say k squared minus 48 times 4 has to equal k times 4. So you set the two pieces equal, but you plug in the x value because we're talking about at this specific x value.
It's kind of like G.
Yeah, this is more function value than limit. Yeah, because we need that to exist and be the same. So I've got k squared. I'm going to bring the 4k over. And then what is 48 times 4? Close. 92.
I said 92.
Oh, I was David, sorry. All right. Yeah.
Is it 4 just because that's like the number that like
That's the x value that we're talking about.
Or do I need to like try?
Anybody? I know, those are big numbers.
4 times.
They're kind of close to each other because they're only 4 apart, right? So it's not 1 and 192, guys, okay? I think you got it. 12 and 16, yes. So it'd be plus 12 minus 16, right? So that we get the right negative sign in there.
Numbers that big.
What? We're not going to do numbers. I just want you to get the idea of what's happening here. So k could equal two potential values. It could be negative 12 or it could be 16, and this would be true. The point is, though, to understand that in your piecewise equation, for it to be continuous, you need the two pieces to run into each other, so that you have to set them equal to each other. Okay? We okay?
Such that the functions are continuous. So we're assuming this is continuous.
Plug it. Get it to stay in there, okay?
So we're assuming this is continuous. Yeah, how those
No, we don't know that. It's only continuous if k is 16 or negative 12.
Wait, it says for number 7 and number 8, find the value for k such that the k is continuous.
Right. We are finding the k value to make these functions
Oh,
continuous. Yes.
Wait, what's that K comma for next?
I like you can see a graph.
This
No, the bottom part.
k equals negative 12 and 16. That's what k would equal. What?
No, the K comma. Is that the other problem?
Oh, that's for 7. Yeah. We're not doing 7.
Oh, okay.
Moving on. Yes.
How do we know that minus 1 and 16 are like the right value?
Because we use the x value of 4, because that's the x value we care about.
Yeah.
And then we set the two equations equal to each other. If they're equal, that means the y values are the same. They're going to run into each other. They would only be equal if k is either positive 16 or negative 12. Okay?
So at 12,
Is it like a what?
wait. So at 12 and 16, they would like, so in the graph, they would like meet.
Yeah. So at like x equals 4, and this is not going to be easy to graph, but let's say it was 16. So the bottom one, 16x, you'd get what? 40, no, 64. What is 4 times 16? 64, yeah. So it's way up here, right? 64, and then it was whatever your slope is going all the way down to 0. That's 64. The other one, if you plug in 16 for k and then 4 for x, you would also get 64, and then it's going that way. Okay. It would do the same. It'd be a totally different graph if we used the negative 12, but same thing, that they would run into each other like that.
The x is less than 4, would that start as an open circle though?
Yes, and then it gets filled in.
Then it gets filled in, so then it is.
Yep. All right, guys, we got to keep going here. So we also have infinite limits. And there's a couple different ways we can talk about these. We're going to go all the way down to this graph in the middle. And let's talk about the left-hand limit of this graph. So your friend is hiking, or maybe they're sledding or skiing now. I don't know.
They're about to be dying.
Where is he going?
Going into the
He went over the falls, guys. It's not good.
He's very dead.
So, guys, what direction is he going, though? Where is he headed? Negative infinity, right? So the left-hand limit, you would tell me negative infinity. But, guys, there's something you have to include with it. Guys, up here. We don't have much time left. Let's get through this. Is negative infinity a defined value? No. So we would also say does not exist. Like, hey, here's the direction it's going, but it's not actually a number. Okay, that's what you're telling me. Yeah. What about your buddy over here from the right?
He's just gonna stop.
He is climbing forever. Where's he going?
I think it's for infinity and beyond.
Let's just do those for me here now.
To infinity and beyond. Yes.
Yeah, I know what you're doing.
Guys, do we see how that's infinity but also does not exist? Okay.
So it says
No.
I say
You say
really don't understand.
Okay, so here's your friend over here. He's following the graph this way. So there's an asymptote right here, so it's just going to keep going up and up and up and up and up. So where's he headed? Okay, you get this part, the infinity. Okay. Yes. The limit does not exist because infinity is not an actual, like, defined value. That's why we agree with that. All right. So guys, next one here. Does the limit as x approaches 3 of x plus 2 over x minus 3 exist? Guys, what does this graph look like?
Vertical asymptote.
Yes. Good. Horizontal asymptote at 1. This is the top heavy, bottom heavy, or equal part. Since they're equal, you just divide the coefficients. But you don't really have to have a beautiful graph here. You need to understand this general shape. So what do you think as x approaches 3? From the right and from the left, are they doing the same thing? They're not running into each other, right? So what are we going to say for the limit? Yeah, which I asked this in a weird way, so I guess no is the answer. Yeah, D and E. Okay? Guys, I don't know why this isn't like bold at the bottom of your paper, but it's very important. Yes, Finn? I know how to graph rationals. Because we did that earlier. Yeah, you got to know vertical asymptotes, horizontal asymptotes. Look back over your rationals. Definitely don't have time today to reteach rationals. Okay? All right, guys. Again, back to left-hand limit, right-hand limit must equal each other for the overall limit to exist. Continuing. We're getting there, guys. All right. Look at this interesting little graph. No, there's really not that much left. What is the left-hand limit of that graph as x approaches 0? Infinity. So we would say infinity, comma, dne, right? What about the right-hand limit? Infinity, comma, dne. So guys, what about the overall limit? What would you tell me? I don't like the way I wrote that. Just what is that limit? What would you tell me? Did they go the same direction? Yeah. Yes. Does it exist? No. So you would tell me both infinity and dne for that. That's like saying, hey, I know both the left-hand limit and the right-hand limit are doing the same thing. Still isn't actually a number, though. Okay?
Oh, wait. What? Not the last page. I'm just kidding.
We're not doing the cosine one because it's weird.
Okay, good.
Flip the page, guys. We can do it. We can do it.
What is that?
All right. Yeah, that is a weird looking graph, right?
That looks like a heartbeat.
Yeah, it does. Something's not going well for this person. Yeah. Oh, goodness. Guys, that is what is called a wildly oscillating graph, okay? It's not just oscillating, it's oscillating wildly, okay? When a graph oscillates like that, meaning it bounces back and forth between different values so quickly, the limit does not exist because it's not like settling in on any nice number for you here. It's just this crazy back and forth. So if you see a wild oscillation of a graph, you can just say the limit does not exist there. This is not something you're going to see a lot, but it is a reason for a limit to not exist. Because of the way it bounces around, there's not. I know you're like, but it would go through this point, right? Shouldn't the limit exist? It's like so aggressive with its like bouncing back and forth that it's not approaching anything. I
I
know.
was gonna say, what's the equation for that?
That's this equation.
Oh.
Yeah.
So.
Okay, so the reason a limit might not exist. The left and right hand limits do not match.
It's just I just I don't have to. It's
Or we could say are not equal.
yeah, like back in 8th grade, it's
We've got 4 minutes, guys. Another way, the function doesn't approach a finite value. That's the whole infinity stuff, okay, right? Because infinity is not a finite value. And the third one, the function oscillates wildly.
oscillates.
Where have you been, Maddie?
Right.
Clearly not.
It's oscillating so much.
So wild.
Because you're wearing a flashlight.
All right, guys. Try number 4 here, A through I. And guys, this is some wild oscillation going on in your graph here, just so you know. What? Well, yes, and that's it. We'll probably do that part as our warm-up next.
Kelly, would you put some heat to do that?
Yeah.
Okay, I can't do it, bro.
All right, guys, letter 4. Get letter 4, number 4. Oh my goodness. Struggle, guys. Letter 4, go. We're ending here, guys, okay? This is it. We're making it.
Oh, it's -2. Oh.
It's too wiggly. It's too wiggly.
Too wiggly.
Too much wiggle. Wait, okay. So, right. There is no. Never mind. I'm too dumb.
Okay. All right, guys. Ready?
What? 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 It's from the right. What? No, I can't read.
The little minuses and pluses are hard to see.
Why are we doing it wrong the whole time?
Are we okay with why letter B does not exist? Too wild.
You're oscillating so wildly.
You're oscillating.
You're oscillating wildly.
Such a wild card.
Oh my goodness. Okay, guys. So I will make your math space available, and that is your homework. Okay.